Signal Sciences is the industry's first web protection platform that works in any cloud, any container, any platform as a service, and any modern application architecture. The Signal Sciences web protection platform can be deployed in next-generation WAF, RASP, or reverse proxy modes, giving customers ultimate flexibility and coverage. Protect your web applications with Signal Sciences web protection platform. Signal Sciences, protecting applications, connecting teams. For more information, check them out at signalsciences.com/PSW. Onapsis is the leading provider of solutions to protect ERP systems from cyber attacks. Customers can secure their SAP and Oracle business-critical platforms from espionage, sabotage, and financial fraud risks. Visit them on the web at onapsis.com. The average time between being hacked and realizing you've been hacked is 1 year. Can you afford to let an intruder roam your network for that long? Can your company weather the fallout when this comes to light? Black Hills Information Security can find the bad guys in your network and train you to do it yourself. Email consulting@blackhillsinfosec.com to find out how a hunt teaming engagement can help you find a persistent threat in your network. Welcome back, everyone, to Paul's Security Weekly. This is our technical segment for this evening. Really quick, besides Kampala, the first B-sides in Uganda. I just been getting that wrong lately. The CFP deadline is tomorrow. So if you haven't submitted your talk, probably by the time you're listening to this in your car, jogging, working at the gym, going about your daily business. I met somebody who was actually the Verizon installer. Was like, I listen to podcasts all the time while I work. I'm like, that's awesome. You should listen to ours. We sent him home with all kinds of stickers and stuff. So by the time you hear this, the deadline has passed. However, the conference will be held in October. So check out bsideskampala.com for updates. Don Pezet from ITProTV is here with us. Don, welcome back to the show.
Hey, thanks for having me back, Paul.
It's nice to have you. I'm excited to talk about random number generators. Before we get started, speaking of ITProTV and learning and stuff, is Mark, are you actually SSH'd into the host that's playing the ads? Is that, or did you cheat? He is. I'm so proud. Mark learned how to remotely SSH in, export the display, run the really insecure Exos Plus command, so that he can execute things in the commercial. And it's all SSH. It's awesome.
Yeah, SSHD all the way.
He cheated his key isn't quite working yet. We're still working on it.
What are you going to do?
He's using the password right now. It's all right.
Should have shared password.
It is actually right now, but that's okay. We're working on it. We're going to have some training, Linux training we're working on.
No, we're working on that too. We're going to get that.
And some Cyber Patriot, hopefully training
Cyber Patriot
training.
On that.
Doug and I have a lot of secret missions that we're working on with Russell and Sam.
Trying to put all kinds of cool stuff together so that more people can enter this field and become, like badasses like all these people that are out there that we keep talking to that intimidate me. So
that's it. We should invite IT Pro down for the thing that we're talking about. Yeah. Don, we'll fill you in after the segment. How's that?
Absolutely.
And random number generators is the topic that Don chose today. Now, I was during the break, I was saying how I used to work for a lottery company. The topic of random numbers was obviously a hot topic. A lot of engineers spending a lot of time on that, obviously, for good reason. You really don't want a predictable lottery number. That would be bad. The one that I liked the best was you get... And this is, you've probably seen videos or heard about this, right? And I don't know if it was ever in practice at a working lottery, but you get a bunch of lava lamps and you plug them all in.
Oh, yeah.
And then you get camovers and you point them at the lava lamps and you base your randomness on the lava lamps and taking pictures of the...
It's on the
movement of
the pixels in the image end up determining a random pattern from this amorphous blob that's moving around in a sort of random way.
Yeah.
And then you get into fluid dynamics and meshing, and you can use meshing algorithms to try to predict the behavior of certain fluids. Yeah. Oh, it's
so turned on right now.
It's a nerd-gasm.
So short of having a room full of lava lamps, Don, what do you have on tap for us today?
All right. Well, I decided to pick as controversial a topic as I could. And if you can't get in an argument over random numbers, what can you argue over? One of the challenges, to build off what Doug was saying, is that it's not good enough just to have a random number. You need to have like a consistently random number. And I know that sounds dumb, like how can you have something be consistently random? But it's really, really challenging. And if you're not familiar with this whole field, I mean, you all should be, right? If you're in security, you should know about random number generation because it's used for everything. Every time you generate private keys for a certificate, you're using a random number generator. And the main problem we have is that computers really suck at generating random numbers.
Yep.
Yes, they do.
And it's, it's software. They can't just think something. Even humans are bad at generating a random number. So they try and come up with workarounds, like Paul was talking about, just any kind of thing they can create. But at the end of the day, most random number generation is done deterministically. So there's a formula somewhere, a program somewhere that is defining where that random number comes from. So we've got to find a better way to do it, because what's built in just isn't good enough. And let me show you an example. Here. We've got a number of different pieces of this puzzle that go together, right? And on a lot of systems, here, I'll bring my system up here. What you'll see is where people talk about dev random and dev/random and dev/urandom, where you've got these two different sources we can pull random numbers from. So if I say like, I'll cat out of /dev/random like that. If I go and reach into it, it's going to pull up a bunch of junk. And I don't necessarily want to do that on my screen, because it'll even pull things like non-printing characters and stuff. That's the random junk that we can generate right out of /dev/random. And
no,
that's
Don, I'm sorry. We just back up for, especially for some of our newer listeners, and talk about random versus pseudo-random?
Okay, sure. So the thing about /dev/random is it tries to be truly random, or as random as we can get, right? But to have a truly random number, you've got to have what's called entropy. It's a pool, right? If I tell you to pick a number, right? You could pick a number 1 to 18 trillion to higher, whatever, it's an infinite amount of choices. But if I tell you to choose a number 1 to 10, it's much easier for me to guess what number you picked, because there's only 10 numbers, right? So when you start coming in and taking something and saying, like, I'm going to, try and pull from this pool of random numbers, but then the random numbers start running out, we have to find some other way to come up with a random number. And people start using formulas and other methods to generate those random numbers, and that's being pseudo-random, right? You're not using this true entropy source. You're using something that is inferior. And that's the difference between /dev/random and /dev/urandom, is that urandom is pseudo-random. And you'd think that's easy. Like, why would somebody use urandom if it's not truly random, right? Why would I ever use pseudo-random? And it comes down to people being impatient, right?
Well, hey, can I put something in there, Don?
Sure.
I'm sorry. You said this was going to be an argument, so I'm putting it in there. There is a purpose for pseudo-random. If you're building simulations, if you're trying to build in computer simulation, one of the key elements of computer simulation, hey, Roger, that's my friend, is that you have to be able to reproduce the result to validate the simulation. I mean, yeah, maybe ultimately you want a random number, but in order to validate your code, you have to be able to reproduce a simulation. So pseudo-random numbers are useful for those kind of tasks. They're not useful if you want randomness, but they're very useful if you just want to do that. Sorry, Don, I couldn't stand it.
No, that's fine. And I mean, we could certainly deviate into a huge argument over this, over like how it's also useful to just use the same password on every system. But
well, if you want to, yeah. Okay.
It really does come down to people being impatient. And let me show you an example here with, I've got an Ubuntu machine I'm going to fire up here, which is Ubuntu 16.04, their long-term. So this is the latest and greatest long-term release from Canonical. And I have really not done anything to this system. So this is pretty much stock as far as that goes, except I installed Terminator because I like that client. So I've got that installed. And on here, I can jump in, and let me kind of change my screen around a little bit here so we can see all this. And what we can do is we can pull how much entropy the system has, and we can start to pull data out of it to kind of see what we've got, right? So, for example, I can jump in here and do something like I can cat out of /proc/sys/kernel/random/ entropy avail, right? And that'll tell me how much entropy I have. And this system only has about 1.8K of entropy. So that's random data that we can yank from to use to then create our random numbers with some deterministic formula. And the deterministic formula can actually vary from OS to OS, but this entropy is a pool of just random crap that we can use to generate random numbers from. Linux, is what I'm on here, usually generates about 4K of entropy, but this system only has 1.8. And the reason is I'm in a virtual machine, and virtual machines have a really hard time generating entropy. If you take a physical machine, like if I were to switch back to my actual laptop, it would probably have maybe 3K or a little bit more because it'll use things like the CPU. But on a basic install like this, inside a virtual machine, there's nothing accelerating it. And so let me change that into like a watch statement here so we can actually watch the entropy pool on this thing. I'm going to pull, we'll do every half a second. Okay. And let's make that big for effect. I need a special effect here. So we're going to pull up, there's my entropy pool right there on the system. Okay. And I can drain that by pulling out of like /dev/random and dropping that into /dev/null, right? So I'm just throwing entropy away. And when I stop, see how the entropy starts to regrow again? But it's regrowing really slow. It's just kind of sitting there. If I wiggle my mouse around, see how that's going up really fast? Well, that's because it's looking for any kind of source of data it can use to generate randomness. And it's looking for CPU cycles, state changes, temperature sensors can be used, lava lamps. It's looking for something to help out, and it just doesn't have it. Well, programmers, that really bothers them because they'll do things like, let's say they need 20,000 characters, 20,000 random characters. So we can do like a head dash and 20,000. And I'm going to yank that out of /dev/random, and I'm going to chuck it into a SHA-256 sum. So I'm just trying to generate a checksum that I can use as my random number, right? Because when you pull out a dev/random, you get all sorts of random stuff. Doing a checksum, that'll give me a nice, alphanumeric value out of it. Now, when I run that, see how my entropy drained out? And now I'm stuck, right? /dev/random is what's called a blocking source. So when it runs out, you wait. You wait for that number to grow back up, and it's going to constantly drain it. So what'll happen is developers say...
So that's why you have to move your mouse and type random keys when you generate keys.
Exactly.
To make up for that lack of randomness.
That's exactly it.
That's a great example of that, Don.
Right?
I like that a lot. Yeah, that's cool.
Yeah, it's a good example of something that's crappy. So,
that's a good way to put that.
Because
that's the foundation for this show, really.
But that was also the reason that we run out of it, because a lot of times in virtual machines, when you have a lot of virtual machines and they're all using entropy all the time, and a lot of times in virtual machines, the entropy engine can't detect the keystrokes because it depends on the drivers.
Right.
So if you have one of those situations and it doesn't detect the keystroke moves exactly, you may run out of entropy really, really fast.
Yeah, and you'll see a lot of hacks that are out there to get around it, right? And pseudorandom is one of those hacks. So, for example, if I ran that same command, but instead of pulling from /dev/random, I pulled from /dev/urandom, right? That's the pseudo-random number generator. And when I run that, I instantly get a result back. But if you notice, my entropy pool did not grow. It just said, hey, there's not enough entropy, so screw it. I'm going to make something up. Yep. And that's what it did. And it turned out okay, right? But it's not truly random at this point. It's deterministic. It was a formula. It's something that could potentially be figured out, recreated, like Doug was saying, and recreated in a bad way if somebody could figure out what we used to seed a private key.
And in your case, it could result from a collision, correct? When you're generating a hash from it, right?
Yeah.
Yep. And there have been examples of this where some versions of the Linux kernel didn't generate enough entropy or didn't refresh it at the right time so that you'd reboot and it would actually generate the exact same entropy after a reboot that it did prior to the reboot. Things like that have happened. And that's the risk.
Another one, Don, on servers, a lot of times there is no keystroke activity. So using a web server that's generating keys for HTTPS and all these kind of things, constantly generating keys. And what happens is that because it's a server and it's sitting there, nobody's touching the keyboard, nobody's touching the mouse, nobody's doing anything, and it runs out of entropy again really fast because it's getting a lot of demand placed on it. And again, then they cheat and they go back and they use pseudo-random numbers, and then somebody figures it out and models it, and then you got a big problem.
And it's hard to tell when they cheat, too, because they could do something like, I'm pulling out our dev random, but what if I didn't even do that, right? What if I just echoed 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 and chuck that right into a SHA-256 sum, which, applications can certainly do. You end up with what looks like a random number, but it's not random. It's really just a polished turd.
Well, and that's been the result. I mean, that last command has been the result of a lot of different vulnerabilities over time.
I've seen programmers do stuff like that all the time, because a lot of times programmers don't know anything about this, and they're just trying to turn the lights on. They're trying to get it to work, and sometimes it's forgotten. They were doing it for their tests, so they were doing it in their beta version, and they forget all about it. And that's the kind of zero-day exploits people find later, is they realize, oh wow, if I just hit this every time, I get the same key back, and boom, I got you. And now you got a big problem, especially if it rolled out to 1 million customers or something like that.
And there's some Linux distros. Now, I'm picking on Linux because it's easiest to demonstrate. Windows has a closed source random number generator, so it's hard to demonstrate. But they all have the same problem. So here, a lot of them have started rolling out other tricks, like the RNG daemon that can run in the background, which I don't have installed. So let me add that in here. I tried to be stock, so this would be fair if anybody tried to recreate my results. But if I just install RNG tools real quick. We'll get that chucked on there. And now what I've got is this RNG daemon that's running in the background that's helping to assist with generating entropy. And actually, my entropy number will start jumping up a little bit faster. It's refilling a little bit faster. But it's kind of funny because they'll advertise things like, hey, you can use your trusted platform module to generate entropy, or you can use your extensions in the CPU to generate entropy. But a lot of times those don't work, or they don't work the way that we expect them to work. For example, on my laptop, I'm running Red Hat Enterprise Linux 7. And in the latest version, they support TPM version 2. But not really. They don't give you the software tools. And so you're not actually generating anything out of that TPM by default. It's there, but the system isn't using it. So it's easy to be tricked into thinking this stuff is working. And if I redo my pull 20,000 characters out of dev random, right now I can run it, and I still see that entropy dropping, even though I've got those RNG tools installed, even though it might think that I have some hardware acceleration, right? Like it thinks I've got the CPU accelerating my entropy source here, but it's really not working. Okay, so that brings me to what I actually wanted to talk about here in this episode was to talk about hardware random number generators. And there's a number of groups out there that have started generating or building these. And it's, this is not a new thing. It's been around a long time. I actually whipped up a slide. I hate slides, but I have one because that's the kind of guy I am. And, basically, I pulled up a list of CVEs that have kind of come from all this. And if you go way back to 2001, that was the oldest one I could find, right? There was a program that generates certs using urandom, which you really shouldn't. Not long after that, you had some SSL scripting that did it. You had the Linux kernel 2.6. That was the one that would reboot and screw up entropy. In 2008, you had OpenSSL that was using an RNG with predictable numbers, right? And it just goes on and on and on. These CVs keep popping up year after year. So the hardware random number generators, what they do is they give you an additional source of entropy. So like this one right here that I have is what's it's called a 1RNG. It's an open source initiative that's out there where they release the plans and everything to build it. And believe me, it's faster to build it than order it because they ship out of Hong Kong. But but you chuck this on your system and you install a little driver, and now this one's acting as an entropy source. It's got a little Avalanche circuit inside of it that uses electrical signals to calculate entropy. But it's not perfect, but it's pretty decent. I've got another one here, which is from a company called Bitbabbler. You can go to bit-babbler.org, which actually I probably have their webpage pulled up here somewhere. But bitbabbler.org, these guys are like psychotic when it comes to calculating randomness. They have really thought of just all sorts of different things to make sure that this is as random as possible. And it does a really good job because it does folding of its entropy. So it's generating really complex stuff. But I want to show you one here at the end of the show that's really impressive. But before I get that far, let me just take that same virtual machine that I was just in that was kind of running crappy, and I'm going to chuck this Bitbabbler on there, and we'll see how this can kind of change and work a lot different, right? So the main thing, well, here, let me get the RNG tools out of here so I get a fair demonstration. And once I pull that out, I'm going to take the Bitbabbler and just kind of chuck it onto this virtual machine, and we'll initiate it to start generating our entropy. And when that happens, we're going to get a much cleaner entropy pool, a much more true random pool of data, and it'll refill almost instantly. So when we yank data out, it's really kind of repopulating very quickly.
And Don, when you says it uses electrical signals, like over USB, it's able to get some of those electrical signals enough to generate entropy from it?
Yeah, in this one, the Avalanche Circuit, what it is, it's like a little gate, and you send electricity to open the gate. Now, we're talking about a very, very small amount of electricity. It doesn't take a lot to power these things. And then just as soon as the gate is about to flip, there's like a little flash point where the energy escapes, and it's actually measuring that escaped energy and using that to generate the randomness. So it's kind of an interesting thing that it does.
That is so nerdy. That is so awesome.
Yeah, it's impressive stuff.
You just said, I thought we were on Star Trek Voyager there, or not Voyager. What's the one you like? Deep Space Nine there for a minute.
Yeah, Deep Space Nine. I like.
All right, so I'm gonna add.
I gotta go back and watch it again.
I'm going to add that one. Let's see. Let me get that one tucked onto the system here, which, actually, I've already got connected. So I just need to fire up the little daemon for it. And, whoops, too many D's on that one. There we go. All right, so now I've got it running, and it's generating entropy into the system. And if I come in and I start pulling out entropy, if I start draining my /dev/random, and sending that into /dev/null. We'll just throw it right away. All right, so it's draining, right? It's going empty there. And then as soon as I stop, see how my pool instantly refilled? That's what the hardware random number generator does. It refills it. It just drops it right back in. So now you don't need urandom. You don't need pseudorandom. When you can pull all you want from /dev/random, get true, clean, well, as true as we're going to get randomness. And now we don't have that risk of hitting a blocking, a pause where we're just not getting our data back.
So, Don, what would be the applications for these USB devices? If I who needs the random so much that they would attach a USB device to it? This isn't a consumer thing unless you're developing software, correct?
Yeah, for consumers, it's not that big of a deal. For servers, right? That's really where it's going to be a big deal. And Doug mentioned as an example, like web servers, where you have SSL, where you're constantly generating temporary session keys. Well, if you're generating those session keys off of something that's not truly random, that's a problem, right? What if the random number generation hardware has actually been tampered with in your system? Like, we know that the NSA intercepts shipments of hardware from vendors like Cisco and tampers with it. So if they've intentionally weakened the random number generator, here's a chance for us to get in and fix that. And they don't have to weaken it all that much. If you just make it where every 10th bit is consistently a 1, now you just made it that much easier to kind of guess the number. Right. So that's the kind of thing that can happen out there and what we've got to worry about. Now, the problem with solutions like this, it's a USB key. If I'm spinning something up in AWS, I can't go and pop a USB key in there. It's not going to happen. And if I've got 1,000 servers, I don't want to buy 1,000 of these keys. I bet Bitbabbler would love that, but it's just, it's too much to manage. But the other thing is, they're not necessarily consistent in between each other. Like, different yields of these USB keys might have varying degrees of quality. And like the lava lamps, right? Not every lava lamp is equal. And so you're not getting consistent randomness out of them. So that's where a company called Whitewood Security came up with a really amazing solution. And let me bring up their little web page real quick. I've got that part.
Quantum entropy.
Quantum entropy, right? I ran into these guys at RSA a couple of years ago, and their product blew me away. It's really impressive because what they did is they got together with a quantum physicist from Los Alamos Labs, and they decided to use photons to generate their randomness. The trajectory of a photon is one of the few naturally random things in nature. So that's what they harnessed. It's really hard to tamper with that. It's really reliable. And they created this entropy engine, right? A little blade like this that you could stick in a server, and then it could act as an entropy source on your network. Kind of like, you use a time server, an NTP server, right? You have this central time server and everybody feeds off it so you get consistent time. Here you can get consistent entropy. And what's really neat is that you can set this up, and then if you build a secure tunnel out to your cloud deployments, they can be pulling their entropy from here. Or they even have a hosted service. But if you're this big into worrying about the the security of your random data, you probably want to buy your own card, to have your own. They call it NetRandom Enterprise. But if you want to try it, they have NetRandom free. You can go to their site, sign up for free, and you can take any machine, install this on here, and it is amazing. And let me just do a quick demo of it here. I'm going to go right back to that Ubuntu machine that I've been picking on. I'm going to kill the Bitbabbler. So Bitbabbler is dead. And I'm going to yank data out of my pool, and I'll see it drain, and I see it slowly climbing back up again, right? And so I'm going to start up my NetRandom client. Okay, so now it's going to reach out to them, and it's going to start generating entropy. And notice, not only did it repopulate my pool, it jumped up to the highest number possible. Linux only generates 4K of entropy, and I'm at 4,095. I can't get any more. So it actually completely filled the pool. And as I start to draw out of it, I'm going to see that pool drain, right? Because I'm sucking data out of it. But as soon as I stop, it repopulates right there. Nice. And this isn't coming from my virtual machine. If I jump back over to their portal, see all this spiked, I'm pulling it from them. And this gives me two advantages. So one, I can connect as many machines as I want to it, and I'm not limited by hardware. And two, because they're all pulling from the same source, it's reliable, consistent entropy. Now all of my virtual machines have a consistent level of entropy that's generated by the same type of source.
Consistent randomness.
I love reliable, consistent entropy. Our entropy is smooth and homogeneous. Yes, it is.
That's awesome.
So getting back to your question of who would use this, if you are consistently generating data that's built upon randomness, and certificates are really one of the best examples of that. If you're running a key server or something of that nature, you really need to be supplementing it with a hardware random number generator. Really, it's a hardware entropy generator is what we're actually dealing with. The random number generator is the same. And in every example I just did, I used the standard RNG that's built into Ubuntu in this case, right? So I was really just changing the source of entropy, and you can rely on your TPM if you've got one and your OS supports it, which a lot of them don't. You can use low-cost devices. I think the one RNG is like $40. You can get a little higher. This Bitbabbler I think was closer to $200. You can go all the way up to something like NetRandom, where it's several $1,000s. But it's all built upon how reliable you need that entropy source to be. There's solutions out there if you just look for them.
And how fast. That Whitewood is actually here, local.
Really?
Yeah, I went to a presentation when he first had the card, and it was a Rhode Island.
It's like a room of lava lamps and a card.
Well, this thing's unreal. I mean, that card is like honking levels of entropy. I mean, yeah, you're getting it off the internet, but this card, you put that thing in there, good luck blasting that thing, because it was unreal. He was like, this is going to serve your whole network. I don't care how big your enterprise is. And he was demonstrating. We actually had the card there. They were demonstrating it.
So using it to generate my SSH keys probably overkill?
Probably, but it sure was fun. I mean, it's like attaching a jet engine to your bicycle, but it sure is cool while it lasts. Right. But it was a really amazing device, and I really enjoyed they actually have a bunch of white papers on their website. If you really want to nerd out, they got a bunch of papers where they show this with math. They show how the quantum photons get generated. Schrodinger's name is used, which always makes me happy. I mean, boing! But I mean, you get into that. It's really exciting if you like that kind of cool, nerdy, super weird stuff. But they have some great white papers, and I was glad you brought that up, Don, because I was wondering if you were going there. And when you were talking about Bitbabbler, I was like, I should bring up Whitewood. But then I was like, was it Whitewood or Blackwood or Whitewater? And I was stalling trying to remember what the name of it was, and then it was like, boom, there you went. And I was like, that's such an awesome card, and it uses quantum, entropy, photons, and some of Schrodinger's theories, and it's like super, super cool. And the math will go like, whew, unless you're really into it.
That's awesome.
Very quick. But it's cool, so check it out.
Well, so Don, if you're listening and you work for the NSA, check out Whitewood's website.
There you go. Don, thank you very much. Are you going to stick around and talk about stories with us next?
Sure, why not?
Okay, so we're going to take a short break, come back, talk about the security news for this week. Stay tuned, don't go anywhere.